Welcome to The Explainer. Today we're going to talk about something more than just code. We're telling a story about a huge problem. How in the world do you build millions of unique, complicated things without completely losing your mind? It's a story about a really powerful idea that, honestly, shapes the entire digital world around us.
Okay, let's just dive right in. This is the fundamental challenge, right? I mean, imagine you're building a video game with thousands of different characters, or maybe a banking app that's got to manage millions of accounts. If every single one of those is just a hand-coded copy of the last one, you'd create an absolute nightmare of code that's impossible to manage, let alone update. This is the exact problem that object-oriented programming was designed to solve.
So to really get what I'm talking about, let's meet this guy, Jack. Jack has this big dream. He wants to build his very own digital car company. But his first try? Well, let's just say it's about to hit a massive roadblock.
So Jack gets to work. He codes his first car, a gray 2-liter 3 Series coupe with leather seats. Looks awesome. But then a customer wants a blue one. No problem, Jack thinks. He just copies all the code and changes the color variable. Then another customer wants a red one, but with a bigger engine. So he copies it all again, changing 2 variables this time. You can see where this is going, right? He is just drowning in files that are almost identical. And if he finds a bug in his engine code, he has to go and fix it in every single file. It is a complete and total mess.
Jack quickly realizes, okay, this is not working. I cannot build an empire this way. He needs a factory, a real system. And instead of building each car from scratch, he has this breakthrough moment. He needs to design a master plan, a blueprint, for a general type of car.
And in the world of programming, this master blueprint has a name. It's called a class. Think of it like the official design document that comes straight from headquarters. Jack creates a class called 3 Series Coupe. Now, this doesn't represent a real car yet, it's just the idea of one. It defines all the things a 3 Series Coupe can have. A color, an engine size, a seat material. These are its potential attributes.
So if the class is the blueprint, what's the actual car that rolls off the assembly line? Well, that's an object. Each one is a specific instance of that class. Now Jack can create a gray car object, a blue car object, and a red car object, and they all come from that one single 3 Series Coupe blueprint. They share the exact same design, but each one is its own unique thing with its own specific details.
A blueprint is a great start for sure, but it's pretty useless without a factory to actually build the cars and a foreman to run the whole assembly line. We need a way to take that design and actually produce a real object.
In programming, this whole process of creating an object from a class is called instantiation, and the special piece of code that kicks off the whole production line is called the constructor. In a language like Python, it has this kind of weird-looking name, __init. Its entire job is to take the order and build the object exactly to spec.
So let's just picture this constructor as the factory foreman, okay? When Jack wants a new car, he doesn't just shout into an empty factory. No, he goes to the foreman. The foreman is the one who takes the order, grabs the blueprint, and gets that assembly line moving to build that one specific car object.
And this is exactly how the order gets filled. Jack goes to the foreman and says, make it gray, give it a 2-liter engine, and I want the proper leather seats. Those details, gray, 2-liter, leather, they become the unique instance variables for that one car object. The very next car off the line might be blue with a 3-liter engine. They come from the same blueprint, but they have different instance variables.
All right, so Jack's digital garage is starting to fill up with all these beautiful car objects. But here's the thing. Cars aren't just static objects that sit there. They need to do stuff. They need to drive, they need to lock their doors, they need to check their fuel. It's time to add some behaviors. These actions, they're called methods. So Jack adds methods like lock doors and get fuel level to his 3 Series Coupe class. And what that means is that now any car object created from that blueprint can perform these actions. So Jack can say mygray_coupe.lockDoors, and the doors on that specific car object will lock. But, this is where Jack hits his first major snag. He creates a gray coupe, and then he creates a blue coupe. He asks the blue coupe for its fuel level, but the program shows him the fuel level of the gray coupe. The getFuelLevel method is totally confused. It has no idea which specific car object it's supposed to be checking. And the solution, thankfully, is a special keyword called self. Jack learns that when he defines a method, the very first argument he needs to include is self. Think of self as a little label that each car carries around that just says me.
So when a method is called on an object, self makes sure that it always refers to the data of that specific object. And just like that, problem solved. The blue car now knows about its own fuel level.
So Jack's feeling good, but then another worry pops into his head. What if some other piece of code accidentally goes in and changes a car's engine size directly, totally bypassing his careful design? This leads him to a core principle called encapsulation. He bundles the car's data, its attributes, and the methods that work on that data all together. And he basically hides the raw data from the outside world. If you want to access it safely, he provides special methods, getters to read the data, and setters to change it in a controlled way.
Okay, so with all these core principles in place, classes, objects, constructors, methods, and now encapsulation, Jack can finally see the bigger picture. He doesn't just have a way to build one type of car anymore, he has the entire system for building a whole automotive empire and doing it efficiently.
And this is where the empire really takes off. Jack discovers the other big pillars of OOP that let you scale up massively. First up, inheritance. He wants to build a high-performance M3 coupe. Well, instead of starting from scratch, he creates a new blueprint that's a child of the 3 Series coupe. It instantly inherits everything, the doors, the seats, the methods, and all he has to do is code the new, more powerful engine. It's maximum reuse for minimum effort. Then you've got polymorphism. This basically means many forms. He can have an accelerate method on both car blueprints. When he calls it on the standard coupe, it accelerates normally. But when he calls that exact same method on the M3, it responds with incredible power. Same command, totally different behavior, all depending on the object. And finally, there's abstraction. Jack decides to design a general vehicle blueprint defining only the bare essentials, like wheels and an engine, that all of his future cars, trucks, and motorcycles have to have. It's a simple, powerful structure for his entire product line that hides all the messy, complex details under a simple interface.
And this really gets to the heart of the matter. It's a completely different way of thinking. Jack's first messy attempt was procedural. His data, the car specs, and his functions, the instructions, were all separate. It was like a disorganized kitchen. OOP is different. It's like having a skilled chef, that's the object, who not only has all their ingredients, the data, but also knows exactly what to do with them. Those are the methods. It's all neatly bundled together. So, why does Jack's journey from this cluttered digital workshop to a streamlined virtual factory actually matter? Why should you care about object-oriented programming?
Well, it's because OOP is basically the engine running under the hood of most of the complex software you use every single day. It's this powerful way of thinking that lets developers manage enormous amounts of complexity by breaking it all down into logical, reusable parts that actually mirror the real world. It makes code easier to build, way easier to fix, and much easier to expand on later. Jack didn't just find a better way to code, he found a better way to think about building systems, period.
So in the end, you see, OOP is so much more than just a bunch of coding rules. It's a mental model. It's about seeing the world not as some chaotic list of instructions, but as a collection of interacting objects, where each one has its own data and its own behaviors. And by organizing our logic around these blueprints and objects, we can build and manage complexity on a scale that would be just otherwise impossible. So the real question is, what blueprints will you design?